I'm Dan Sweeney from MathSpec Incorporated. A common fallacy is that in order to identify an unknown analyte using mass spectrometry, the first step is always to determine the molecular formula. In this video, I will demonstrate that a compound can be identified without first knowing its molecular formula using our Excel add-in. In this example, getting the molecular formula will be our last step. This diagram shows the process that our Excel add-in uses. First, the accurate mass fragmentation data is converted into multiple partitions of the accurate mass of the analyte. These partitions each consist of 3, 4, or 5 imaginary subfragment masses. Each partition is scored based on how many fragment ions can be assigned using different combinations of the subfragment masses and how intense those assigned fragment ions are. The mass of each subfragment is then converted into subformulas. The PubChem compound database can also be searched if one or more subformulas can be converted into SMARTS notation. In this demo, I will use substructure searching. Many smaller subformulas generated using the Excel add-in correspond to only a few substructures, but these substructures are usually very common. For example, searching the entire PubChem compound database for compounds having the substructure corresponding to a methoxy group will either just stop after 1 million hits or time out. To make substructure searching more practicable, scientists at the National Center for Biotechnology Information recently developed fast substructure searching, which limits the PubChem search space to a small subset of PubChem compound. Fast substructure searching has now been incorporated into our Excel add-in as a new worksheet called Search Within. I will use this mass bank spectrum of thiazopyr as an example. The mass spectral data from the group at the University of Luxembourg is always excellent, and they generated thiazopyr spectra at 6 different collision energies. What I like about this spectrum at CE30 is that there are many fragment ions over a wide mass range, and yet the precursor ion at 397 Daltons is still present. The best spectra for identification work are spectra, like this one, that have multiple fragment ions and yet still have significant precursor ion intensity, because as the collision energy increases and the precursor ion disappears, the probability decreases that subformulas found with our Excel add-in will match substructures in an unknown analyte. To save time, I've already entered the data into a new Excel workbook. There was no isotope ratios available of the precursor ion, so I calculated those using the isocalc formula. I'm going to use all the default parameters. The data was positive. Now this analysis might take a few minutes, so I'm going to pause the recording while this is running. So it's completed the transform. If I expand this bottom part here, go to data input, it took 275 seconds, about 4.5 minutes or so, to generate this results here. The partition scores look pretty good here. The first thing I usually try to do is go to the summary page and select the precursor, the neutralized precursor mass. And then sort by mass error. And when I look at these formulas, there are quite a few possibilities. I'm doing this demo to show that you don't need to get the formula, but this is usually the first thing I look at. The other thing we could do, for example, we could take this formula is used twice, so let's take this one. We can copy this into the isotopes page and paste it in, and then let's say we had a orbit trap and we had MS data at high res. So we could generate the where the protonated mass would be for this particular compound and the first and second isotope data. We could go back and do that for maybe 4 or 5 of the of the formulas that have the lowest mass error, and then compare the experimental to the estimated isotope ratios that we get here. But let's go back here to usually what we would try to do also is go to the search within page and put in that formula if we're happy with a particular formula, and then we could generate a catch of all the compounds in PubChem with that formula and a text catch key. Now in this case, if we look at partition 1, there are a great deal of formulas. The reason is because the one subfragment mass is 276. So there are an awful lot of formulas that will work for 76.07 plus or minus 3 millidaltons. That was our mass error. But the other four subformulas are pretty consistent with 3 hydrogen fluorides and a C2H4S. If we look at some of the other partitions here, this one's very similar, but it's, if you will, divided the compound up in a different way. So now we have instead of 3 hydrogen fluorides, we've got 2 and a methanol. So let's go and just take, in this case, the first set of subformulas, copy it, go to search within, and I want to zip over a little bit, and we want to do a transpose, and we could then try to generate smarts substructures for some of these smaller subformulas. And then we could repeat that with the one that has a methanol instead of an HF. But since these are from the same molecule, if you will, what I can do is just go to partition 2 and copy that subformula, go back to search within, and I'm just going to paste that in here. So basically now we have 5 smaller subformulas, and I'm going to try to generate smart notations for these. Go back to add-ins. There's a icon over here on the left side. I'm going to click on that. What that does is it looks in our Excel add-in to try to find, oh, I can't do it that way. I can do it this way. So it tries to find a corresponding smarts notations. And these are searchable in PubChem. Now I need to have a catch, a subset of PubChem. And in this case, since we don't know the formula, I'm going to use Entrance, and we have to go back again to partition 1, and let's get the mass here. This would be a calculated mass from the fragmentation data. This was the neutralized mass here. And I'm going to copy that, go back to PubChem, paste, put a colon in, paste it again, and we want to do a monomolecular mass. The function we need is MMAS, and we want to go plus or minus 3 millidaltons, so this would be 89 and 95 over here. So let's search that. So we have 8,973 compounds in with that mass, plus or minus 3 millidaltons in PubChem. Now I want to generate a cache in PubChem that will be available for a number of hours, like at least 4 hours or so, that we can now search with our Excel add-in. So I click over there, and then this is our text cache key. So this is a key to those 8,973 CID identifiers. Copy that, go back to Excel, the search within, and for the cache key, instead of using all the compounds with a certain formula, I'm using all the compounds with a certain mass range. Okay, and then we need to generate a hyperlink. I'm going to try to just copy this, or you can type it in, of course. Okay, so this is a hyperlink, and what we've done is we've taken these smarts that correspond to various subformulas, and we've combined them with a period in between, which means it's a different part of the molecule. So we're looking for something that has 3 hydrogen fluorides, a methanol substructure, and also a C2H4S. So let's follow that hyperlink. Okay, so it's because that text cache key, it just searched those 8,900 compounds, and it's saying that this compound is the only one that satisfies all those conditions of mass and subformulas. See if I can get back to the PubChem. Whoop. Okay. So the compound that fits is thiazopyr. It is, I could say that it's very unusual to limit it down to one compound. Usually you'll get up to 100 or so compounds that may fit all those criteria, and they're usually sorted by PubChem by relevance. So now we can get the formula. It's C16H17F5N2O2S. So in this case, we identified the compound, or what appears to be the compound, and then we were able to get the molecular formula. This is a brief summary of some of the functions and hyperlinks that are found in our Excel add-in. Well, I appreciate your watching this video, and I hope you'll try this approach with your own data. Thank you.